All right, this lesson is 7.3, Solving Exponential Equations. If you're studying the Pre-Calculus 30 curriculum, it's in your textbook on page 358, 7.3. But anyways, we're going to be exploring how to solve exponential equations. And I just want to outline a couple things, first of all, that in the previous sections we've been studying exponential functions. Okay? Those are different than exponential equations. So let me remind you that in a function, we have y and x. And together, there will be partner values, x and y, points, x and y, that will form a graph, right? So we have a whole bunch of points that when you plug x in, you get these y values, and together, all of them form something that is recognizable from these previous sections, and that is an exponential graph, okay? So there are many, many partner values here. Input an x value, you output a y value, okay? And that goes onto the graph, x, y, all of these points, okay? So that's a function. This, of course, is the base, and here's x and here's y. Now, the equation's a bit different. We don't have x and y, but we have something, you know, like a typical equation, where you have something, a value, equaling another value, but part of this is unknown, and so we have to solve an equation. So just like, you know, 3x plus 1 is 7, and you try and find the x value, right? Except the x value is in the exponent position. So there are a few tricks or a few methods that we're going to look at here in this course. Two of them we're going to study today. Some things that you must know before we begin. Okay. So each base number, okay, so I'm talking about a base number like in the examples here, base number 2. Okay, that's the base. This is the exponent. This is the value, okay? Each base number has many powers, and so when I say powers, I mean this whole unit right here. This is a power. So again, base, exponent, power. And there's many powers that are associated with each base. So for example, 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 cubed is 8. 2 to the 4th is 16. So all of these numbers here are associated with one base. That is the base 2. The only thing that's changed is the exponent, okay? That's important. First thing you need to know. The second thing that kind of comes from that is that many different numbers can be written with the same base. And that's just the reverse of what number 1 is. So 27, 9, and 1 all have a property in common, and that is that they can be written with the same base number of 3. The exponent is the only thing that changes. See that? So 27 is 3 cubed, 9 is 3 squared, 1 is 3 to the power of 0. So these two things will help us to use method 1 in solving exponential equations. All right, so the first method is solving exponential equations using like bases. Okay, so let me explain how this happens. In our first example here, here's a typical equation, and you can just look at this equation right now, and you don't have to, I know you don't have to do any work, you don't have to show any work, you just know that x equals 2. Okay, you know that just by looking at it. But when we get over to this one, it's maybe a little bit more complicated. You can't look at that and say, I know what x is, okay? Maybe you can. But they're going to get tougher. So let's explain what I mean on a simple example. So 4 and 16 each have the property that they can be written with the same base. And actually there's two bases you could use. I'll show you both. 4 can be written as, well, 4. A base of 4. So we would leave that. And 16 could be written also as a base of 4. Okay? Now, if you look at this equation, you see that this is almost identical. And when the bases are identical in an equation, that means that the exponents must also be identical, okay? That they must equal each other. If the bases equal each other, the exponents must equal each other. So that is a very important little note. So I've just written this down here so you can look at this later. You can write this down in your notes if you're taking notes. It says in an exponential equation, if the bases are equal, and of course we're talking about where there's only one single term on each side, but if the bases are equal, their exponents are also equal. So if the bases are equal, the exponents are also equal. So I'm just going to clean this up a little bit. And what we can do now is we can say, all right, now the 4's are the same base, and so I'm going to let x equal 2, and I'm going to solve that. Well, guess what? It's already done, and that's how you solve a simple exponential equation, by using like bases. Again, you could have done this in your head, I know, but this is why you did this. This is why you did this in your head, because you knew that 16 was 4 squared. 4 to the power of what gives us 16? You knew that. And so we're just simply writing it out, showing our work, and explaining why you could do this in your head. So let's take that over to this next example, okay? Now this is going to be a little bit tricky, but you look at 1/3, right? And you look at 27, and you ask yourself, can these be written in the same base? The answer is yes, although 1/3 maybe looks a little tricky. We can write both of these in with a base of 3, and let me show you how that works. How can you write 1/3 with a base of 3? Well, if you remember negative exponents, 1/3 is actually written as 3 to the negative 1. So you rewrite this as 3 to the negative 1. You leave that x there. And over here, as we mentioned just a few minutes ago, 27 is actually 3 cubed. Okay? Now be careful, x is not equal to 3. You have to simplify this. Exponent laws say that if you have a power raised to a power, you multiply. So this is 3 to the negative x equals 3 cubed. Therefore, negative x equals 3, or x equals negative 3. That is your answer. So I'll let you just digest that for a second. All right, this one's a bit tougher. Again, yet again, it's a bit tougher. So let's see if we can do this. 27 and 81. Well, we know that 27 can be written as a power of 3. Can 81 be written as a power of 3? And the answer is, of course, yes. Now, you may need to write down on the side of your paper somewhere, just as a reminder, some common powers of 2, 3, 4, 5. You might need to do that. So you may need to do something like this that I just quickly did on the side. That was too quick, wasn't it? Awesome. Anyways, what we can see here is that 3 cubed is 27. So let's do this. Let's write 27 as 3 cubed. Okay? And I'm going to leave that 1/3 there. And then I'm going to write 81 as 3 to the 4th. And how do I know that? Well, 27 times 3 again. So 3 times 3 times 3 times another 3 is 81. And so we have 81 is actually 3 to the 4th to the power of x over 3. So that's your first step. When you can, this won't always happen, right? There are other methods that we're going to use, but when you can write them as similar bases, this is a nice, straightforward, easy way to go, and you're going to have to know how to do this. So we simplify this now. That becomes 3 to the power of 3 times 1/3, which is just 3 to the power of 1. This becomes 3 to the power of 4 times x over 3, right? Or, 4 over 3, 4x over 3. Okay. So now that we have the same bases, you let 1 equal, or you can do 4/3 x, or whatever you want to do there. I'll write that a little bit differently. To get x by itself, you can multiply by 3, then divide by 4, or just multiply both sides by the reciprocal. And you get x equals 3/4. Okay? So, let's just try that. Okay, so on the calculator here, if we just test this side over here, 27 to the power of 1/3 is 3. And over here, 81 to the power of 3/4 divided by 3, and be careful with your brackets here if you're testing this on your calculator. 81 to the power of 3/4 divided by 3 is also 3. So we've got the correct answer here. Okay, that was a bit tougher, but again, that's how you do that. Rewrite with the same base and then solve a simple algebraic equation. Okay, the next thing we're going to do, this is method 2, solve by graphing. And in this case, what we have is we have a simple equation again. It's the same one we started with. Very, very easy. And what you can do, just like we've done in other sections, with other equations, you can graph two separate functions and find out where they intersect. So you're going to graph the first function, which is y equals 4x. And you're going to graph that out, find out all of the points, okay, that make up this exponential function. Then you're going to graph y equals 16. And you're going to notice that this is a horizontal line, right? Cutting through y equals 16. And then you're going to find the intersection point. So why don't you take a minute right now and with your graphing calculator and do that. Alright, so here we are in your graphing calculator. If you haven't done this yet, 4 to the power of x is going to be your first one. And simply for the second function, y equals 16. I've adjusted my window a bit, so if you want to adjust your window so you can see things exactly the way I'm going to see them on the screen, here's the window. X min is -1, max is 6. Y min -3, max is 20. And you get this for a graph. Okay, so that's the y equals 4 to the power of x, exponential function. And there's the y equals 16, okay, the constant function. And the solution is going to be exactly where this intersects. Now, it's not going to be the y value because we know y is 16, right? But it's going to be the x value. And you can even see here without even doing any calculations. 1, 2 looks about where this is going to intersect. And that's exactly what we're looking for. So on your calculator, if you need to see this, again, this is how you find the intersection point. Second function, trace. Option number 5. Your calculator will ask you if this is the first curve, and you can't really, so the cursor's off the screen, so let me just bring that to the screen. First curve, yes. Second curve, yes. And intersection point, hit guess. And there you have your intersection point. And of course, the x value, right, that we're looking for is 2. And that's how you can use graphing to solve an exponential equation. And of course, if the exponential equations are really complicated and difficult, the graphing calculator doesn't care how difficult a function is as long as you can type it in properly and adjust your window, I guess, so you can see the intersection point, because it won't calculate if you can't see it. And you use your x value, and that's your solution. You may have more than one solution, I guess, on some things, but on the exponential function, you should just have one. All right, I'm going to do one quick example. Time's running short, so I'm going to do this fairly quickly. You can pause the video if you want to read this through, and then I'm going to show you how to do it. Solving by graphing. Okay, so here we have our values. You've read the question. A value here, okay, is the amount of money at the end of the investment needs to be $5,900. The P, the principal, is $5,000. The interest rate per period is 0.0153, and we're going to solve for n. So here is your equation, your exponential equation, and we are going to graph both sides. I'm going to graph this, and I'm going to graph this on the graphing calculator, and we'll calculate the intersection point. Okay, so if you put your equations in like this on your calculator with your window, something like this, you're going to get a graph that looks like this. Here's your solution.